Dear friends, we are going to study the very important concept of continuity of a function. Before going to this topic, the concept of continuity, I would like to remind you about the limit of a function. So, dear friends, let's start. First, we know about the functional value of a function, then limiting value of a function. So first we consider a function, let it be f of x equal to 3x plus 1. Now we shall find the value of f of x at x equal to 3. Then you just put the value of x equal to 3 in this function. Then we have f of 3 equal to 3 into 3 plus 1 is equal to 9 plus 1 equal to 10. And this is the value of the function at x equal to 3, and this is called the functional value of f of x at x equal to 3. Now we shall find the limiting value of the function f of x equal to 3x plus 1. Okay. Now consider its values at a point very close to x equal to 3. We can approach x equal to 3 from left hand side as well as from right hand side. We shall take the value of x very close to 3 from left hand side, as well as we can take the value of x very close to 3 from right hand side also. Here table 1, in table 1 x approaches 3 from left hand side. In table 2 x approaches 3 from right hand side. Okay, so here you see if x value is equal to 2.9, then the value of the function is equal to 9.7. If x value is 2.99, then the value of the function is equal to 9.97. If x equal to 2.999, then the value of f of x equal to 9.997. Now you see, when we approach 3 from left hand side, the f of x approaches to 10. You see, first 9.7, then 9.97, then 9.997, which is very close to 10. So we can write, when x tends to 3, f of x tends to 10, right? In table 2, here you see x approaches to 3 from right hand side. So first you take x equal to 3.1, then the value of f of x is equal to 10.3. If x is equal to 3.01, then f of x is equal to 10.03. And when x equal to 3.001, the f of x equal to 10.003, and which is very close to the functional value of the function, that is 10. When x approaches to 3 from right hand side, the function approaches to 10. Yes, here you can see here 10.3, then 10.03, then 10.003. When x value approaches to 3 and when x value is very close to 3, that time the function is very close to the functional value of the function, that is f of x tends to 10. Understood? Now we take another example. Let f of x equal to x square minus 25 whole divided by x minus 5 be a function. Now you find the functional value of f of x at x equal to 5. If you put x equal to 5, then you get 5 square minus 25 divided by 5 minus 5, that is equal to 0 by 0, which is not defined. So here functional value is not defined at x equal to 5. Now come to limiting value of this function. Now we consider its value at a point very close to x equal to 5. We can approach 5 from left hand side as well as from right hand side. Here you see x values is very close to 5 from left hand side. Here you see x value very close to 5 from right hand side. When x equal to 4.8, the value of function is equal to 9.8. When x is equal to 4.9, the f of x equal to 9.9. When x equal to 4.999, the functional value at 4.999 is equal to 9.999. Now you see, when we approach to 5 from left hand side, the function approaches to 10. Similarly, you can approach from right hand side. Now x approaches to 5 from right hand side, and here x value is very close to 5. So when x equal to 5.2, the value of f of x is equal to 10.2. When x equal to 5.1, f of 5.1 is equal to 10.1. When x equal to 5.001, the value of f of x at 5.001 is equal to 10.001. So when we go closer to 5, the f of x tends to 10. When x tends to 5 from left hand side, the function tends to 10. This is left hand limit. When x tends to 5 from right hand side, f of x tends to 10. This is right hand limit. Understood? Type of limits: left hand limit, right hand limit. When x approaches a from left hand side is called left hand limit. When x approaches to a from right hand side, we say right hand limit. And left hand limit is denoted by limit of f of x when x tends to a. Here, limit of f of x when x tends to a from right hand side. So this stands for approaches or tends to. We can approach to a given number a on the real line either from its left hand side by increasing numbers which are less than a, or from right hand side by decreasing numbers which are greater than a. From right hand side which are greater than a. Now left hand limit LHL, we can write f of a minus 0 is equal to limit of f of x while x tends to a from left hand side is equal to limit of f of a minus h when h tends to 0. Like this we can write for LHL. The statement x tends to a minus means x tending to a from left hand side. That is, x is a number less than a but very very close to a. Okay, therefore x tends to a minus this is equivalent to x equal to a minus h where h greater than 0 such that h tends to 0. Similarly, right hand limit you can write like this: f of a plus 0 is equal to limit of f of x while x tends to a from right hand side and limit of f of a plus h when h tends to 0. Right hand limit can be written as this or this or this. So the statement x tends to a plus means x is tending to a from right hand side. and x is a number greater than a but very very close to a. Therefore, x tends to a plus this is equivalent to x equal to a plus h, where h greater than 0 such that x tends to 0. Okay, so right hand limit you can write like this or like this. Okay, now functional value of f of x at x equal to a, the functional value. So this is functional value. Now come to existence of limit. What are the conditions for the existence of limit? So limit x tends to a, f of x exists if both left hand limit and right hand limit exist. So left hand and right hand limit must exist. First condition. Second condition is left hand limit is equal to right hand limit. Otherwise, limit does not exist. So these two conditions must be satisfied for the existence of limit. Now come to uniqueness of limit. If limit x tends to a, f of x exists, then it is unique. Only one. There cannot be two distinct numbers L and M such that when x tends to a, the functions tends to L and M. So when x tends to a, the function tends to L. If limit x tends to a and function tends to M, then they must be equal. L must be equal to M. That means limit x tends to a, f of x is unique. Okay. Example 1. So that the limit of the function f defined by f of x is equal to modulus of x divided by x if x is not equal to 0. Then f of x is equal to 0 if x equal to 0. Now we show that the limit of this function does not exist. Okay, first we find left hand limit, then right hand limit. If they exist, then we check whether they are equal or not. So left hand limit. Limit x tends to 0 from left hand side is equal to, we can write limit h tends to 0 f of 0 minus h. Then limit h tends to 0 f of minus h. So we can write now limit h tends to 0 minus h mod by minus h is equal to, mod of minus h is h. So limit h tends to 0 h upon minus h, that is equal to limit h tends to 0 h cancel, so minus 1 is equal to minus 1. Similarly, we shall find RHL, right hand limit. So limit x tends to 0 from the right hand side. We can also write limit h tends to 0 f of 0 plus h is equal to limit h tends to 0 f of h is equal to limit h tends to 0 h modulus divided by h is equal to limit h tends to 0 modulus of h, h divided by h. So h cancel, so limit h tends to 0 we get 1, so 1. Now you see left hand limit and right hand limit, are they equal? Left hand limit exists, right hand limit also exists. Now we see the second condition, whether they are equal or not. Now you see left hand limit is minus 1 and right hand limit is plus 1. So LHL not equal to RHL. So the limit x tends to 0 f of x does not exist. Okay, see. Limit of a function. Here we know the epsilon delta definition of limit. A function f of x is said to tend to limit L as x tends to a. F of x tends to L as x tends to a. That can be written as limit x tends to a f of x equal to L. For any arbitrary positive number epsilon, however small, there exists some positive number delta greater than 0 depending upon epsilon such that f of x minus L mod less than epsilon. Whenever 0 less than x minus a mod less than delta, that is, if x belongs to a minus delta a plus delta in this open interval where x is not equal to a. That means a minus delta less than x less than a plus delta and x is not equal to a, then L minus epsilon less than f of x less than L plus epsilon. Note: limit x tends to a, f of x should not be understood as substituting x equal to a in f of x. In fact, f of x may not be defined at x equal to a. That is, the point A may or may not belong to the domain of f of x. So, we are not to check the difference of f of x and L at x equal to a, because 0 less than x minus a mod. For example, f of x equal to x square minus 1 whole divided by x minus 1. Clearly, f of 1 is equal to 0 by 0, which is meaningless. That means f of x is not defined at x equal to 1. If there exists delta greater than 0 such that a function f of x is not defined on the interval a minus delta a plus delta minus singleton a, then the question of limit of the function as x tends to a does not arise.